Okay. Hello. Am I audible? Hello. Mm, can anyone confirm? Am I audible?
Yes, good evening, sir. You are audible, sir.
Okay. Okay. Thank you. So in today's session, we'll be discussing about the week eight content parts. So how many of you have gone through the week eight content? Just raise your hand. Okay. Only one. Okay. Great. So week eight is basically a data structures part only. Okay. So same thing you are going to learn in your PDSA course as well. Lot more detail. So here we have few important things which we are focusing on for the DBMS course. Okay. So first, like if you go to the content, we have some linear data structure. Then we have discussed various search, linear and binary search, and then we have magnetic disk storage part is there, and then we have few buffer replacement policy, right? So as a part of this particular for this particular course, what I can say, just focus on the magnetic disk part in this particular week, and then we have binary search tree, right? So BS tree. So you need to focus on that part as well, right? Rest you can go through the content, and yeah, the same thing anyway. You are going to learn a lot more in detail in PDSA course. Okay. So yeah, I hope this is fine. So in this video, I will quickly summarize about what is linear search, binary search, and then we'll discuss in detail about the binary search tree because that is an important topic. And then if you see practice assignment question, you have one question based on the LRU and the MRU, right? Least recently used buffer replacement policy and most recently used. So what is that? Which type of question you can expect and how to solve? We'll discuss this in session. Okay. Okay. I hope I was audible, right?
Yes,
Okay.
sir.
Great. So tell me, what do you understand by the linear search? If anyone, in general, you can say, like, okay, how many of you have done PDSA course? Okay, no one. Okay, no worries. Yeah. So first, suppose we are storing a data in the form of array. For example, let's say, yeah. Suppose I have this data in my array. Let me create one thing here. Okay. Let's say, for example, 2, 3, 4, 1, 7, like this. Okay. So I have this particular array. Now I want to search whether 1 is present in this particular array or not. So how we are going to search using a linear search? First, what is linear search? As name suggests, linear search, right? So anyway, you are going to discuss that thing in detail in PDSA course, but as a part of this course, let's have an introduction about this linear search. So, like how we are going to come? Okay, so first tell me if you want to find out whether one is present in this particular list or not. How we are going to do? What process you are going to follow? Forget about this. What is linear search? What is binary search? In general, what process you are going to apply if one is present in this particular list or not? Yes, anyone?
Sir, we can compare with each element.
Okay. So what we can do? We will take first element, we'll compare whether it is equals to 1 or not, our required element, right? So if that is true, then we can say, okay, my element is found. If this is not true, then we'll go for a next element. In this way, we'll compare every element from this particular array and we'll see whether it is our required element or not. So in this way, I will compare 2 equal to 1, no. And compare 3 equal to 1, no. Check for 4 equal to 1, no. Here you can see 1 is equals to 1, right? Now my this condition gets satisfied here. Now I can say, okay, now 1 is present in this particular list or array. So this is, in simple term, we can say a linear search, right? So you can see here the algorithm start with the first element, compares with the given key value, and returns s if they match. Okay, so our key value is basically a 1 in this particular case, and we are going to compare this key value with each and every element here in the case of linear search, right? So this is how we can do a search in the case of this linear search algorithm. So here you can see what we have discussed in the case of a lecture. So same example. So here you can see we have input array. Just 1 minute. Okay, so here you can see we have input array and we have stored in the form of this array academics, right? And then we want to find out whether I is present in this particular array or not. So same thing we are following here. In the step one, we are comparing whether this particular element is equals to I or not. If it is not, then we go for a next one like that, right? So in this way, we'll compare the key, the required a key with each and every element like this. And here we can see we will found a particular key. So we'll say, okay, this is true, or yes, the key is present in this particular list. That's it. So simple concept of linear search, as name suggests, we are going to search the key in a linear manner. Okay. So as of now, just understand this particular case, and you can see a Python implementation of this for the linear search. Same thing we are doing it here. Now, suppose let's say instead of this, I have this particular array. Okay, 1, 2, 3, 4, 5. Now this is sorted array, right? So this array is sorted in ascending order. You can see. Now here I want to search whether 3 is present in this particular list or not. Now in this way what will happen, right? So suppose I want to see 3 is present in this list or not. So first again I will compare with the first element, second element, and here I can find out, okay, 3 is present, right? So in this case what is happening here, even I know if my array is sorted, but still I am searching it sequentially like that, right? So the time complexity will be what in this particular case. So when we talk about time complexity, as of now, just understand. So how much time it will require to search that particular element, right? So in the worst case, what will happen in this particular linear search? My this element 1 is present at the last here. For example, let's say I want to find out whether 10 is present in this list or not. So let's say 8 and 10 here like that. So in the worst case, my element can be at the last. So it will take n number of element to search, right? But what if I already sorted this particular array and then I'm applying the search, right? So in the case of linear search, still it is going to be the same. But now what is binary search here, right? Okay. First, any doubt in linear search? Simple concept. Simply we are searching for a key in this particular linear manner. So one by one we are comparing. That's it.
Sir, excuse me, sir. One query, sir.
Yes, tell me.
Hello. Yes, sir. So what do we mean by the key term, the term key when we use key? What does it
Search.
signify?
So which element we are going to search in this particular array? That is what we are calling it as a key. Search key.
Okay, sir. So the element we are talking about.
Yeah.
Element is the such.
So whatever the element we want to search, that is basically a key here.
Okay, got it. Thank you.
Yeah. Okay. Now this is about the linear search. A simple.
Will we, excuse me, sir,
Yes.
will we be arranging it in ascending or descending order?
No, for linear search it is not required,
Okay.
right? But anyway, even if it is in the ascending or descending order, sorted order, but still we need to compare with each and every element, right? In the case of linear search, this is how linear search works. But can we think about a different case? If I have a sorted array, in that case, what we can do? So, for example, I know that let's say I have this much thing. Let's say we have few more elements. Let's say we have 6, we have 7, we have 8 as well. Now I want to search for my search key is basically what? 6, right? Now in this case, what will happen if I apply linear search? One comparison, second comparison, third comparison, fourth comparison, fifth comparison. At the sixth comparison, I will find that particular element, right? Sixth. But I already know this particular element is sorted. So can I apply a different technique here to search this particular key? Okay, so here number of comparison is basically what, 5, and here you can see like n number of comparison, 6. For a 6 comparison, I'm getting that particular element. Now, what about the binary search? Suppose I have this particular array in a sorted manner. So how we can apply a binary search here? So binary search is applicable to only case where we have a sorted array. So you can see here in the case of binary search, the input for the algorithm is sorted list only. If the list is not sorted, then first we need to sort in the ascending order, and then we can apply binary search, right? Otherwise, we cannot apply binary search to an unsorted array. Okay. Now, how this algorithm works? So see, first we need to sort the algorithm here. You can see, then algorithm compares a value, that particular key value, with the middle element in the list. So same thing. Suppose if I want to search for a 6, right? So here you can say how many elements are there? 8. So how to find out middle of this particular element? With their index position, you can find out, right? So here you can see if the key matches, then it returns the index particular value. So if does not match and it's greater than the middle element, the new list is the list to the right of the middle element here, right? So if I take this particular example, if you see, index value is starting from, let's say, 0, 2, 3, 4, 5, 6, 7, right? Yes. Any doubt, anyone? Okay. So see here, we are giving the index value to this particular thing. Now, what happens in the
Hello.
case of binary search? We yes,
Hello? Hello?
yes.
Sir,
Uh,
what is the difference between list and array?
the difference between list and array.
Yes, sir.
Okay. So see here, when we talk about the array, right? So array, we can say all elements are having the same data type, but in the case of list, the element can be of different data types as well. And also when we talk about let's say, for example, in terms of size, so we can say array is having the fixed number of size. Once I define, let's say, the array of size 8, so it can take 8 elements. But in the case of a list, it is dynamic. I can keep adding the elements, so it will get increased, right? So if we talk about in terms of programming, so in Python, if you see, this list is basically works as an array. Okay, so we can say that it is an inbuilt function in Python, right? So in Python, this basically list is basically one-dimensional array. You can say like that, 1, 2, 3, 4, like that. Okay. But as of now, if you want to understand a difference is that array is of fixed size, list is dynamic. Array can have like all the elements should be of same data type. In list, we can have different data type. Like for example, 1, then we can have A, B, again then 2, like that also, right? So in Python, when you see here again, this list can be considered as an array as well. Okay, so don't get confused here. As of now, just understand that array is basically a fixed size and list is dynamic in nature. Okay, that's it. Okay, so yeah, so if I want to apply a binary search here to this particular thing, so what we need to do first we are going to find out the middle element. How to find out middle element? By using the index position. So 0 plus 7, that is 2, that is basically 3.5, right? So we'll take the ceiling value here. So let's say, for example, floor 4 we are taking, right? So what happens? Let me check the algorithm what we are doing. Do we have Python implementation? Yeah, here you can see floor values we are going to take. The floor value of 3.5 is basically what? 4. So index position 4 is what? Here, this particular thing, 5. So we are comparing whether the element at this particular position is greater than the key element or not. If it is greater than the key element, it means what? I don't need to search on this side, right? So my element is not present on this particular side if it is greater. If that particular element is less than this particular key value, it means what? My element is present on the left hand side of that particular middle element, right? So I don't need to search on the right hand side. So in this way, you can reduce the time for searching, right? So simply now what will happen? I will compare fifth whether it is equals to search key or not. That is not true. then I'm going to search only on this particular site. That's it. Now I will compare, I will take this particular list now. So again, I will find out the middle element for this. That is 4 plus 7 divided by 2. That is basically what? 11 divided by 2. So floor value will be what? 6 here, right? Like this, 5.5. So again, the sixth element is what? 7. Again, I will compare with 6 and 7. No, it will be on the right side here, right? Left side. So again, in this way, I will take the element 4 and 6. So 4 plus 6, that is 10, 5. So fifth element will be what? This sixth one. I will compare the element at fifth index position, that is 6, with my search key here. That is basically 6. So here I found the element in my particular array. So here I can say it will return the true, or it will return the index value at what index value that particular search key is present, right? So that is basically a 5. So what we are doing here, we are breaking down the problems here, right? So if you see this particular code, how we are implementing binary search here, we are taking that input array. So whatever the array we have, we are taking that search key as an input. Now we have some variable low equals to 0. Then we have one variable high. So we are initializing this with what? The number of elements. So length will give us number of element in that particular array minus 1, right? So mid equals to 0. And now we are starting the while loop here, you can see, right? So whenever low is less than or equals to high, we are going to do this particular operation. So mid equals to high plus low, divide by 2. We'll take the floor division here. Then again we are checking if the middle element is less than the search key, then what we are going to do, low equals to mid plus 1, means we are going to search from this side, from lower value to the middle value. But if the middle element is greater than the search key, it means what? We need to search new list to the left of that particular k value. Okay, sorry. What we are doing here? Yeah. If the middle element is less than the search key, right? Yeah. If the middle element is less than the search key, it means what? We need to search on the right side of particular k, right? If the middle element is greater than the search key, then new list is to be left of k. This is what we are saying here, right? And this is what we have done here, right? Else, otherwise, we can say the element is present at that particular position, and then we are going to return that particular index value. Otherwise, if that element is not present, let's say for example 10. Now 10 is not present. We have done all the operations here. What will happen? It will return -1 if the element is not present, right? So same thing is applied here as well. You can see in this particular case. So given input is like this. We have this particular array and search key is I, right? So by using the binary search, first we find out the middle element. We compare d equals to I. No. Then we find out the middle element of this one. So I is the middle element here. And then we compare whether I is equals to I or not, right? So this is how we can perform the binary search, right? That is how this binary search works, and we will get the element. It will return the index position of that particular element. Okay. So anyone, any doubt in
So why are we doing length minus 1?
here? Because
Yes.
if you see, the indexing start with what? 0, right? So if I say this 1, 2, 3, 7, 8, right? How many elements are there? 5, right? So length of this
5.
particular array will be what? 5. But at index position, how many will be there?
Okay, 4.
5 minus 1, right? 4. So we want to iterate to this particular position, right? So that's why length -1 always in the case of list. Okay. Okay. Great. So please keep a note of this Python implementation of binary search. It will be useful in your Python course as well as DBMS course as well as PDSA course as well. Okay. Anyone, any doubt in linear and binary search? Simple concept. Linear search, I think everyone understand. Simply we are comparing the element with every element, and we are seeing whether it is equal to that search key or not. If it is equal, then we are going to return that index value. That's it, right? In the case of binary search, what we are doing, first we are sorting that particular array. Once we sort the array, then we are applying the algorithm and we are checking whether it's equal to middle element or not. So first we are finding out the middle element. We are comparing with the middle element. And if the key value is greater than the middle element, then we search on the right side of middle element. If key value is less than the middle element, then we search on the left side of the middle element, right? So this how we this repeat will get repeated unless we found the key. If we didn't found the key, that particular search key, then we'll return -1. Okay, that is not found.
So if the middle point is a decimal number, I
Now
mean a
then we are
floor,
taking the floor value. Okay,
then we take the.
upper value, floor value, floor
Oh,
division is there, right?
okay, okay.
So here 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So 9 divided by 2, that will be 4.5. So floor value of 4.5 will be 5. So 1, 2, 3, 4, 5, as you can see. Okay. Or indexing start with 0, no? 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Anyway, here it will be 4. Yeah. Okay. In the case of like this, we can go with the floor value. You can see here floor division. Okay. Great. Anyone? Any doubt now in binary search and linear search? Okay, great. Now next we have what happened. Okay, so you can go to lecture
Sir,
8.1 and 8.2 like that.
sir,
Yes, tell me.
am I audible?
Yes, yes,
Sir, why we are learning binary and linear search in DVMS?
so here, if you see the next topic, that is basically indexing, right? So in that you need to know how the searching is happening here. Okay, in the case of indexing. So if you understand how binary search works, then you can understand the concept behind the indexing part.
Okay, sir.
Okay, now the next is basically if you talk about a non-linear data structure, that is basically a graph, or we can say a tree, right? So let me check that part. Yeah, so you can go to the content part here. You can see. Okay. Yeah, so we'll discuss about this graph non-linear data structure here, right? Yeah, so you can see this graph consists of what? Edges and vertices, right? Here you can see this graph and vertices, right? Now, graph can be of anything. So it can be undirected graph or directed graph. When I say directed graph, it means what? From one node, we have this particular arrow to another node, right? That is basically what? Directed graph here, right? Weighted or unweighted graph. So if we have some weight, like from the cost corresponding to go from A to B, will be some weight there. So we'll mention on that particular arrow. So that is basically weighted graph. If there is no such case, no weight is there, that is basically unweighted graph, right? Cyclic or acyclic. So if you see this particular thing A, then we have B, then we have C, then we have D. Let's say we have this particular node like that, right? So if cycle is present in this particular graph, then we can say cyclic. So if you observe here from A to B, we can go, but from B to C we cannot go. But here you can see A to D we can go, D to C we can go, and again I'm coming back to A. So here we are forming a cycle. In the graph, if we are getting this particular thing, that is basically what? This is a cyclic graph. If the cycle is not present, then we can say a cyclic graph. Okay, simple. And this connected disconnected graph is basically this one. Okay, and we have discussed about the ER diagram part. So we can say it is basically a graph, but every node is different in that case. Okay, we have entity, we have relationship like that, right? Each is having its own specification. So that is basically we can say a complex graph in that case, ER diagram part. So for instance, in Facebook, it uses the graph database, right? Then knowledge graph is also basically a graph data structure, right? So this is about the graph. But what about the trees, right? So what is tree here? We can say it is a connected acyclic graph. Whenever we say tree, it is what? Acyclic graph. It means cycle is not present in that particular graph. Okay, it is also graph, but it is acyclic graph, representing hierarchical relationship here. You can see. So you should know the notation of this all those things. So if you talk about this particular first node, right? So what we can call this particular first node here?
Roots,
Yeah. So you can
sir.
see here, this is basically my root node, because from this only we are getting all the branches, right? So these all are basically what? This, 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 where we don't have any further node, right? For all this element, what we are going to call this?
Leaf, sir.
Tree structure. Yes, that is basically a leaf node, right? So we have this root node, we have this leaf node because we don't have any other branches here, right? We can say it is a leaf node. And what about the remaining node?
Parent and child
Internal
nodes.
roots, sir.
Yeah, we can say these are the internal node, or we can say non-leaf node as well. Okay, so here we can see this DF, it is not mentioned, but DFH are also the leaf node only here. Okay, now one more thing, parent and child node, right? So if we talk about the parent node here, so for example, this A is a, if I talk about A as a parent node, then children will be what? B and C like that, right? Similarly, if we see B is a parent node, then children of B will be what? D, E, F, right? So I can say B is basically a parent of E, B is basically a parent of D and F like that, right? So except the root node, every node is having the, what we can say, parent node. Can we say like this? Except the root node, every node is having some a parent node, right? Even the leaf node is also having this particular parent node like that, you can see. And what are the children node? So if we consider this B as a parent, then children of B will be what? D, E, F, right? So node which is descendant of a node is basically a children, you can say. So D, E, F are all the children of node B. Similarly, I, J are nodes of I, J are the children of this parent E like that. Okay. So simple nomenclature of this particular tree. So main thing is root and child. Sorry, main thing is root, leaf, and what is non-leaf node. Okay. I hope this thing is clear. Any doubt in the tree part?
So we are going to use this in the physical or the logical part.
The logical part, right? So no, here we are discussing how data is stored actually, right? Indexing part you can see here.
Okay. So in the schema, we are going to use data structures.
Yeah. So if we see the first week, we have view level, logical level, and we have physical level, right?
Yes, yes,
So in physical level, we discuss how the data will be stored at the database, right? So at physical level, how which
yes,
indexing we have to use. So these all are the discussion happens for the physical level. In logical level, we discuss about the design part, ER diagram part is there, right? So ER diagram part
yes.
comes in the logical level, but how actually data is going to store at the disk, That is what a physical level is. So indexing, we can say it's a physical level. Okay.
So this is a part of logical level.
No, here we are discussing the concept, how these different data structures we have. Okay.
Uh, yes, we are
Index,
going to use this in logical level, no? Data structures.
no, see, we are discussing the concept, okay, how these data structures are there, right? BS tree, B tree, B plus tree. For that purpose, we need to understand what are different data structures we have, linear and non-linear, okay? Then we are storing in that particular fashion. So we are discussing the concept right here. Yeah. Okay.
Okay, sir.
Okay. Uh, yeah. So we have few more nomenclature here, very important. So internal node, we can say node which have at least one child is called as internal node. So we can see this at least one child, right? So all are internal node except this leaf node, because leaf node don't have any children, right? What is subtree? We can say subtree represent the tree rooted at that particular node. Now, what does this mean? If I say the subtree of this node C, so H will be a right subtree. This entire thing will be a left subtree of this particular node C. For this node A, this entire thing will be a right subtree. This entire thing will be a left subtree, like that. Okay. The subtree represent a tree rooted at that particular, for that particular node, we can say. Okay. So siblings, you can say having the same parents, we can say siblings. Not that important, but you can keep the nomenclature. Arity, very important. Number of children of a node. So if you see for this particular node, how many children this we have? Three. So the arity of this particular node will be what? Three. Similarly for G, we have two children here, right? Like that. And similarly for E, we have two children here. It's the number of children of the node. That is what arity is. And if you talk about the leaf node, they don't have any children, so arity will be zero, like that. Okay.
So what
Now,
is path node? Path.
which one? Path. Okay. The path refers to, for example, let's say I want to go to J from A. So by which path I will go? By which node I need to explore? So first from A I will go to B. From B I will go to E. From E I will go to J. So A, B, E, J. Right? This is the path I got from A to J. If I want to go to J from A, so this is basically a path, you can say, of node, right? So path refers to sequence of nodes along with the edges of a tree. So you can see sequence of node I have visited to reach that particular node J. First I have visited A, then B, then E, and then J, like that. Okay.
Okay, sir.
And we
Path
have,
can be more than one, no?
yes, path can be more than one, correct. We can reach this particular J, this particular node by different path as well. Okay. Here it is simple tree, but in other cases we can also have multiple paths as well, and for that we have different algorithms to find out the base path as well. Okay. So that is not a path, that is not a that is not covered in our course, so we'll not discuss that thing. But as of now, just understand
Oh,
what is a path here. Path refers to sequence of nodes along with the edges of a tree, like that. Okay. Okay, now this is the basic nomenclature we should know about the tree. Now, what is this levels, height, and binary tree? These are the very important one, okay? Because we'll be discussing questions, so we'll be using this particular terminologies now. Now, when we talk about the levels, right? So, if in the for this DBMS course, what we are saying, if the root node is always at the level 0, right? Unless it is mentioned in the question that consider root node at level 1, you need to always consider that it is at the level 0 only, right? So always assume that it is at the level 0, unless it is mentioned in the question that root node is considered at level 1. Okay. So root node is said to be at level 0. Then we can say this at first level, we can say. So level 1. This will be a level 2, and this will be a level 3. Okay. So you can see here the root is said to be at a level 0, and the children of the root node are at level 1, and the children of the nodes which are at level 1 will be at level 2, and so on like that. Okay, so this you can say hierarchy thing here: level 0, level 1, level 2, level 3, like that. Okay, now what is the height of a tree? Okay, so you can see level is the length of the path, number of links or distance of a node from root to from the root node. So level of A is 0, yes. Level of C is 1, yes. Level of G is 2, yes. Level of J is 3. That is basically correct. So what this particular sentence is saying, when we talk about the level, it is giving what? It is giving the idea, the distance of that particular node from the root node. For example, when I say level of K is what? 3. So it is at a distance, we can say height 3 from this particular root node A. Okay, like that we can say. So now what is height here? So we talk about the level, right? So maximum level in a tree. So what is maximum level in a tree? That is level 3. So here we can say 0, 1, 2, 3. So height will be what? 1, 2, 3. So we can say height of a search tree is what? Height for this particular tree is what? 3. Okay. So in short, you can say maximum level in a tree is basically what your height is, right? When it start from 0. Okay. If it is starting from 1, then in that case it will be a different. So remember this particular thing. If in the question it is mentioned that consider root node is at the level 1, in that case answer will be different. Okay, so this will be level 1, 2, 3, 4. In that case height will be still a 3 only, but in that case it will be L minus 1 here. Okay, but here we have height equals to maximum level in that particular tree. Okay, now we have discussed about the levels, we have discussed about the height. Now what is binary tree? What is binary here? So binary means what? Two, right? So
True, true.
each node can have at most two children. So we can say at most. So either 0, 1, or 2, right? So it has arity of 2. Arity means what? Number of children it can have is basically a 2, right? So what is binary tree here? So if I draw a binary tree here, so every node will have at most two nodes. So we can see this is my binary tree like that. Okay, every node will have at most two nodes like that. It can be possible that this node don't have any other node, only one node, or you can see in the leaf node we don't have any children. That will be 0, right? So this will be my binary tree. Every node is having the at most two nodes, right? At most two children, you can say, right? This is not a binary tree here, the given example, right? For A, it is satisfying, but what about B? B is having three children, so that is not the correct. So each and every node in the tree must have at most two children, right? That's it. So you can check here. We'll discuss a lot more in
So
detail.
E is binary.
Which one?
E.
Yeah. For this, you can say E having two nodes, so it's satisfying the condition of for binary case. Okay. So but binary tree is what? Entire tree we can say binary tree when each and every node will have at most two children. So this
Okay.
tree is not a binary search tree because of this particular case. Okay. So here you can see few important facts, very important. You can keep a note of this. Okay. If we have a tree like this, okay. So what we can say in general? What is fact number one? A tree with n nodes will has n minus edges. If you see how many nodes we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 nodes. So the edges will be what? N minus 1, that is basically 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Okay. So fact number one, if tree is having n node, then it will have n minus 1 edge. What is fact number two? Maximum number of nodes at level L of binary tree is what? 2 to the power L. So we are talking about binary a tree here, right? So if you understand, this is a binary tree, right? Now let's say this is level 0, level 1, level 2, and let's say this node is also having two, and this node is also having two children like that, right? So this will be my level number 3. Okay, L3. So how many maximum number of nodes we can have at each level? The maximum number of nodes at level L in the case of binary tree is what? 2 to the power L. So the first you can see we can have only one node. At second we can see we have two nodes. At the uh, third level, that is second, L equals to 2, we can have at most 4, right? Here we have 3, that is fine. Again at this particular point you can see here at most how many things we can have to the power 3, that is basically 8, because here we just have the nodes corresponding to this one, right? But if we talk about this node as well, you can see at this particular point at level number 3 we have 8 nodes, at level number 2 we have 4 nodes, right? So maximum number of nodes at particular level in the binary tree is what? 2 to the power L. So you can expect a question, small question on this, like suppose consider we have this number of nodes and this level. So how many nodes will be present at this particular level in the case of binary tree, right? So simple formula you should remember. Now what about the fact number 3 here? So we are saying that if h is the height of the binary tree of n nodes, then what? So these things are true. What is this condition here? H plus 1. So what is h here? Height, right? So height plus 1 will be always less than or equals to what? Number of nodes. This thing we already discussed, right? If you see height for this is what? 1, 2, 3, right? So 3 plus 1 is what? 4, right? So this will be always less than or equals to n. Now, why equals to? Can you tell me in which case this will become equals to? Less than you can understand in this case, because if we have like this, right? So it will be always a less than. But when it will become equals to, can anyone tell me when this condition will become true? H plus 1 equals to n.
Sir, when
Yes, anyone?
every node will
When
have
there is
only
no
one
child.
Every child.
every node will have only one child.
Okay, so every node will have one child. So we can say in this context, right? So we have this skewed binary tree like that. We can say, let's say for example this. So here what is happening? 2, 3, 4, 5. So level 0, 1, 2, 3, 4, 5, right? So height of the search tree is 5. And how many nodes we have? 6. So h plus 1 is less than equal to 6. Yes, 6 is less than equal to 6. So in this particular case, we can say a worst case scenario, this will get satisfied. Okay. So remember this point. And again, this n will be less than or equals to what? 2 to the power h plus 1 minus 1. Okay. So less than equals to 2 to the power h. What is h? Again, height plus 1 minus 1. Okay. So very important thing from this particular slides, all these three facts, and this one is very important, right? If you see any exam, you can see, like if you know the gate data science exam in gate 24, it was a question directly, right? It was one of the options, you can say.
But if level is not considered at 0,
Yeah.
Root node is considered at 1, then this h plus 1 will become only h, na?
In that case, h plus 1 will become h. Yes.
Yeah, okay.
So, and this rule is for the entire tree. What if there are is this is only for a binary tree?
Yeah, this is for only for binary tree, you can say. Yeah, for binary tree node n. So every node is having only two children, then only we can say at most two children.
One or two? Yes.
At most two, yeah. So you can see here this logarithmic of n plus 1 minus 1 be less than equal to this particular things, right? So you can just keep a note of this important things, fact 1, fact 2, fact 3. Okay, so that's it. But I hope you understand what is a binary tree here, right? So how we are going to store a data in the binary tree? Let's discuss that. Let's say I have this data 2, 3, 1, 8, 5, 7, and let's say 10, right? We have this 7 element, right? Let's say one more thing, 9. Now, in this particular sequence, we need to insert the element in the empty binary search tree. So this is our example for, okay, for example. Now the first element is what? 2. So I'm going to add 2 at the root node here, right? Now how this tree is created, binary search tree. Let's say we have one particular element, let's say k. Okay. Now the next element will be what? What are the next element we have? If that element, let's say for example I, if that element I is greater than this particular key, then that will be stored on the right side. Okay. But if that element is less than this particular key, then that will be stored on the right side. Okay. This is how binary search tree is constructed. If any element is less than that particular root node, it will be stored on the right side of, sorry, less than means it will be stored on the left side of that root node. If the element is greater than that of root node, it will be stored at the right side of that root node, right? So we have an example as well here of binary search tree. So you can see here, let's take this order only. What happened? The binary search we have applied here. Yeah. So here you can see binary search tree. So the value of each node in the left subtree is less than the value of its root node. Here you can see like that. Similarly, the value of each node in the right subtree is greater than the value of its root node, right? This is about the simple binary search tree, okay? So always remember this particular case in the case of binary search tree, how it is constructed, right? So let's try to create a binary search tree for this particular sequence. Now first element is what? 2 here. Now where the 3 will go? What is my next element? 3. So where I need to insert the 3 here?
To the right.
Right.
Right, sir.
Right. So I'm going to
Right.
compare whether 3 is greater than this 2 or not. Then only I'm going to add on the right side here. Then my next element will be 1. Again 1 will be where?
Left.
Again compare
Left,
whether 2 is greater than
left
whether
of
1 is
2.
greater than 2. Yeah, but no. So that will be on left of 2 like that. Now 8. Tell me where 8 will go?
Right of 3.
So 8 is greater than 2, so right of 2. Again, we need to compare 8 with 3. So again, 8 is greater than 3, so again, right of 3. That will be like this. Okay. What about 5? Where 5 will go?
So left of 3.
Left of 8.
Left of 8 or 3 or 2.
Left of 3. Sir.
So it's less than
Left of 8.
8.
Yeah. So again, we are going to compare 5 with 2, that is greater than 2. So it will be on right side. Again, compare 5 with 3. It is greater, so it will be on the right side. Again, compare 5 with 8, that is less, so that will be on the left side here, right? So what we are doing here, we are comparing the element, we are comparing that particular element with every node here. If it is greater, it will go to right. If it is less, it will go to left. That's it. Okay. Now what about 7 here?
Right of 5.
Right of 5.
Yes.
Okay. So see here again, 7 greater than 2, yes. Greater than 3, yes. Greater than 8, no. Less than 8, so it will go on the left side of 8. But what about 5? It is greater than 7, sorry, greater than 5, yes. That will be like this. Okay. What about 10?
Right of 8. Sir.
Right.
Right of 8.
Greater than 2, greater than 3, greater than 8, greater than 8, that is 10. What about 9?
Left of 10.
Again compare,
Left of 10.
yes, 3, yes, greater than 8, yes, greater than 10, no, that will be on the left. That is basically 9. So this is what the resultant binary search tree will look like for a given sequence. So once we have given the sequence, you should be able to you should be able to construct a binary search tree like that. Okay. So I hope you understand this particular thing. Now based on that, you can expect a question, right? What are the root node? What is the leaf node? So what are the leaf node in this case? Tell me.
1, 7, and 9.
179, right? Then we can say what is the height of the search tree?
5.
4, sir.
5.
4. 1,
4, sir.
2, 3, 4. Right? So level 0,
Okay,
1,
4.
2, 3, 4. So height will be 4, like that. Right?
Okay.
So the thing is, you should be able to construct a binary search tree. That's it. Now, once you construct a binary search tree, then we are going to ask a question like, what is the tree? What is the height of binary search tree? How many elements are there on the left side of node 8? What are the leaf node? What is the summation of left subtree elements of that particular node, like that? But the main important thing is what you should understand how to construct the binary search tree and few nomenclature like what we have discussed, right? That's it. Okay. Anyone, any question here?
So if whether we call root node as level 0 or level 1, heights are not going to change, na? Heights are
Height will
starting
be,
from second level only, right?
yeah,
Means
height will be 4 only for this case.
But if the root is considered as 1, then
Height will
4.
be
Okay,
4
5
only.
minus
Yeah,
1, 4.
that will be 5 minus 1 in that case. Yeah. If you are starting the level from 0, then maximum height will be equals to the maximum level. Sorry, height will be equals to maximum level. Okay.
but then if height is not going to change, then our formula h plus 1 becoming just h. If root node is 1, that will change, no?
Yeah. So
Or
that's why here you can see in this case, no.
yes, here h is being taken as l or what? So that's
No, here we are considering H as L. So height is basically maximum level. So considering root node at 0. Okay, root node at 0. So unless we mention the root node at equals to 1, so always assume that the root node is always at level 0. Okay, unless it's mentioned in the question. Now in PDSA
so if
course,
root
there
node
might
root node is 1, let's say if root node is equal to 1, then the height next to the root becomes 2, huh?
no, height will be 1 only. Level will be 2.
Okay, but then in this formula what should we put? The formulas of h.
Okay, so here you can see in this case what is our H, that is basically what 1, 2, 3, 4, that is basically equals to L, right? Now here if we start from 1, in that case my height will be what? Height will be same 4, but in terms of L, what is that? 2, 3, 4, 5. L minus 1, right? You can say. So here you can see here if we are putting this as H, right? So this will be entire thing will be what L in that case. If you are starting from uh, what 1, level 1. Okay.
Okay.
Okay. So hashing part we'll discuss in detail, model 44. So simple thing. We discussed the plotting in detail, but you can just go through the basic. That is good enough. Yeah. So we have discussed few more examples like what we discussed. That is basically in terms of integers. Now, also you can see this particular string we can insert in the binary search tree like that. Okay, in alphabetical order we are going to insert like that. Right? Okay. So again, how to search the key in the binary search tree here. So again, you can see here we are going to consider what is the root node and what is that key. Okay. So first again we are comparing with the root node. If it is equals to that particular element, then that's it. Element is found. Otherwise, if it is on the lesser than the root node, we'll go to a left side tree. If it is greater than the root node, we'll go to a right side tree. Right. So in this way, we can search the element into the binary search tree. Right. So here you can see a binary search tree. Then we have different types of binary tree as well. So I guess we have not covered in this case. Yeah. So we have different types of binary. It's AVL tree is there, and balance tree, basically AVL tree only, right? So those are the different types of binary tree. It is not a part of the course, but you can explore, right? Now, what we have discussed in the case of binary search tree, why we required that, right? So search key in the binary search tree is of order h, where h is the height of the key, right? In the worst case, what will happen? This is the worst case, right? Let's say, for example, this particular skewed is basically a worst case. Now, whatever the element I want to search is at this particular position, right? So again, I need to compare each and every node. So in the worst case, the time will be what? That is only the same thing, order of n, right? But what is about the best case scenario? When we talk about the best case scenario, this will be like that. Like that, okay? So in this case, if I want to find out this one, so I will just compare with this one, after that one, after this one, like that. I am going to get the search key, right? So in the best case, the time complexity will get reduced to what? Order of log n. So you can remember this two important point. In the worst case, it will be always order of n. In the best case scenario, it will be a order of log n. Okay. So this is about the
So
binary
this log is
search.
based to the base 2. This log.
Just log to the base 2. Yeah.
Okay.
So in fact 3, the three conditions you gave, the second one was l- ceiling level of log of something.
Which one?
Up, can you scroll up?
Mhm.
Uh, uh, the three conditions.
This one, fact,
Yes,
right?
yes, sir.
Hmm.
Yes, sir. So log of n plus 1. Uh, so this is also important. Second and third condition.
Yeah, yeah. You can keep a note of this as well. Okay. But remember, this is for the binary search tree. Okay. And here we are considering, uh, because anyway we are not going to use a level anywhere here. L is not there, so this will be the same case, right? In terms of height and number of nodes.
So here n is the number of nodes.
Yes, number of nodes. Okay.
Okay, so are we going to have numericals based on this?
No, no. You can just remember this particular comparison. That's it, right?
Okay.
Yeah. So
So K-nary
yeah,
is means it's a binary.
yeah. So number of node that particular, so number of children that particular node can have maximum. So when we said about this one, this will be a binary, right? So you will have two thing like that. So log to the base 2 here. Okay. If we are having two at most children of a particular node, so binary tree here. So order of log 2 like that case. Okay. So k tree is there. If we have three children for every node, in that case we can see here, right? Log to the base 3 in that case. But this will not be the case. Every node will have 3. Okay. So
But this is a
remember a
binary tree, no?
yeah, here k equals to 2, that is the binary tree. Okay. In general, we have specified that for a k tree,
Okay, okay,
it will be
yes.
like this: log n k, base k.
It
Okay.
can
So
be other than binary also.
yeah, but in that case, every node will have that much number of children, k number of children. Okay, like that. But the best use case is of binary tree only. So remember this only. Okay. If you see in next week 9, we discuss about indexing part, where we'll discuss about B and B plus tree as well. Okay. So that in that you will understand the concept of all those things, right?
Okay, sir.
Okay. Great. So I just want to understand how what is the tree data structure and how binary search tree works. Okay, and how to construct a binary search tree if we have given the required elements, and based on that we should be able to find out. We should be able to construct a tree and find out the answer for the given question. Okay. Okay, and then there can be the same binary tree for a different sequence as well. Okay, this is also possible. Suppose if we give one particular graph, so there are possible that a different sequence can have the same binary search tree as well. Okay,
So
so
can a number repeat in the sequence?
number.
Can any
Okay,
number repeat in a sequence?
no. In this case, what we consider key, right? So every element is unique here because if I want to search, so I will go to the particular element directly, right? So I will compare with two this three, right? So we are considering the every elements are unique here, right? So key is basically unique here, right? We are
So
considering like that.
can there be two eights here?
Two?
8 or 2 5?
No, we are considering it as a unique element only in this particular
Okay,
example. Yeah.
okay, okay.
Because we are going to
So,
use this for a search key, right? So keys are always unique, right? We'll see.
okay, sir.
Yeah. So we are
So,
going to store the data at this particular pointers, right? So we should know, we should have a unique value for that. Yeah.
but the value can repeat, but the index can differ, no? So, there can be duplicates, no?
No, in the array in the list we can have duplicate, but when we talk about the binary search tree in the sequence, we are considering it as a unique element only. Okay, for constructing a binary search tree.
Okay, sir.
Okay, so this is about the binary search tree. We have few examples in the practice assignment or grade assignment. You can just go through that as well. Now, if you see, let me check. There are few important topics. Rest you can just go through the content. This physical storage part is very important when we where we discussing the magnetic disk. So just note down the formulas where in the tutorial what we have discussed. So based on the formula you can solve any question. Okay. Anyway, we are going to discuss that in the Saturday's session. No worries. But two important things are there. Let me check where it is. How we are going to store the file organization. Then we have buffer replacement policy. You can see there is one question based on that as well. Lecture 8.5. Yeah, buffer manager, buffer replacement policy. Yeah. So in short, we have discussed here, but we have a question based on this, so that's why we need to discuss in detail. So here you can see we have two different techniques, right? For example, we have a buffer storage and we are storing the element into that particular thing, right? Buffer storage, right? So how, suppose if I want to add, if I want to allocate a new element to that particular buffer, so which element we need to remove that, right? So for that we have few things. So most operating system replace the block based on the LRU strategy. So how it works, what is LRU, what is MRU, right? That is most recently used strategy. We'll discuss one example based on that, right? So in the buffer, we are processing one block at a time. So if we have a storage of, let's say, for example, three, like that, right? And it is already occupied, it is already full, four, five, six, like that. But if we have a next page we say next we say element or page we can say here, right? So let's say for example 8. So where we are going to store that, we don't have which element we need to remove so that we can add this into a buffer state. So how we are going to remove the element from this particular case? For that we have these two things, LRU and MRU. Okay. So just remember the name, what is LRU, what is MRU, and based on the name only you can solve the question. Okay. So let me take the example from the practice assignment only. So that will be easier to explain. So please go to the lecture. Okay. So whatever I have discussed, it will help you to solve the problems, solve the assignment questions. But why we are doing that? For that, professor has explained in detail. So please go through that. Okay. Mm, Here it is, question number. Yeah, you can see question number 10 of practice assignments, or 10, question number 14. Yeah. Okay. Is my screen visible?
Yes, sir.
So here,
Sir, zoom, please.
uh, yeah. Now, yeah. So let's say we have something to store, right? Let's say, for example, we are storing this particular block. Okay. Sometimes we call it as page also. So let's say we have a considered string of pending block references in the given order. So this is a given order, right? 3, 4, 1, 4 like this. So these are the blocks we can say, block number. The system has a buffer with 3 slots. So we have a buffer storage having 3 slots in that like this. Okay. So initially it is empty. So initially the buffer is empty. Now if I want to store this particular block number in the buffer storage, how we are going to do that? And if the buffer gets full, which element, which block to uh, remove? This is what we are going to discuss. Now here if you see, we are applying the LRU buffer replacement policy. Now what is LRU? Least recently used. Now what do you understand by least recently used? This particular name.
Means the usage was very old.
Yeah.
It
So
was not
among
recent.
those, yeah, among those three block, which block was recently used? Means least recently used. So yeah, the one we have used at the last, right? That is not at the last, at the initial step we can say, right? So least recently used, right? Old one, yeah. So initially the first element is what? 3 here. So I can add the 3 here, right? Then the next element is 4. Anyway, we have a storage, we have a space, we can add 4. 1 is again is there, so we can add 1 in the buffer, right? So now here we can say all the 3 slots got full. Now my next block is what? 4. Now if you see here, my already that particular block is present, right? Now here comes the concept of hit and miss, or we can say fault as well. Okay, page fault. So what is hit? What is miss? So once we added the blocks inside the buffer, now if we go for a next block, now if that block is already present inside the buffer, then we can say it is a hit. Means what? 4 is already in the buffer, so we can say hit 1. So for this particular element, this block is already present, so we can say hit 1. Now we are not going to do anything. So this is for 3, 4, 1. For the next element was 4. We got hit here. Now my next element is 2. Now we have this one 3, 4, 1. So which element out of this 3 was least recently used? Now we are applying the concept of LRU because now my buffer is full. So which one is least recently used?
3, sir.
So you need to check this particular thing. I am at this particular point. So among this, which one is least recently used?
3.
3, right? So I'm going to remove 3 and I'm going to add 2 here. So that will be 2, rest would be like that only. What about the next element 3? Tell me. Now we don't have 3 in that. So now which will be a least recently used element here?
1.
Out of this 2, 4 and 1 we got. So again you can see 1 was the oldest one. We have used that. So we are going to remove the 1 now, and instead of 1 we'll put 3. So 2, 4, 3 here. Now what about 1? Again 1 came, right? Again the storage is full. Now which element we have to remove here?
4,
So 1 is there, right? Among this one, which one is the oldest one?
4,
4, right? So we need to remove 4, 2, 1, 3. Next element is 4. Now again
Re-
storage is full. Which element we need to remove?
2, sir.
2,
We are doing it for this element. From you can see which one is recently used. One we have just which one is least recently used. So we have used this, and oldest one was 2. So we need to remove 2 now. 1, 3. So see, you require some practice for doing this. Otherwise, you will get confused what we are doing here, right? So please try to solve few questions like that. Because after 4 we have this 2, and let's tell me now which element I need to remove because I don't have any, because I don't
3.
have 2 in that. Which one is least recently used? 3 here, right? So I'll remove 3. So 4, 1, 2 like that. Now next element will be what? 3. Tell me.
1,
So 2, 4, 1. So 1 was recently least recently used. So we'll replace like that. 4, 3, 2. So that's it. In the last we will have this particular thing. So how many misses? Misses means what? A hit means once we have the element inside the buffer, that we'll consider that as hit. So only one hit we got out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of 10 element, we have one hit. And how many misses? 9 will be the miss. Okay. So how many misses we have? 9 will be the answer in this case. Okay. It means what? Whenever the block number is already present inside the buffer, then we can say it is a hit. That's it. Okay.
How 9, sir?
Initially, if you see here, it was empty. For 3 also it was miss, right? We have entered 3. Then for fourth also it was miss because we don't have any other element we have entered. For 1 also it was miss, right? So 3 misses was there. Then fourth one will be this 4, 5, 6, 7, 8, 9 like that. Okay. So for this 3 misses will be there. Now, initially empty. So 1 for 4, another one for 3, another one like that. 3 misses we have.
So, sir, first the order was 3, 4, 1.
Huh.
Then when it was a hit 4, so 4 becomes the
Recently used element.
recently used, and the least recently used will be 3 and 1 then.
3 and 1. Yes. Okay. So instead of 3, 4, if we have 4, 3, 1, 4, in that case, which one will be least recently used once we hit the 4?
3 only.
Then
4,
3 will be there. No, once we enter the 4, 4 is already hit, right? So if I want to insert a 2, so then 4 is already hit, right? So out of this one, 3 was the least recently used, so we are going to remove 3. Okay. So least recently used. So you need to check the order for the element you are inserting in this particular manner like that. Okay. So please try to solve few examples because in quizzes in end term you can expect a question like this. Simply a sequence will get changed and number of misses, number of hit we are going to ask. Okay, like that. So simply if element is present, hit, otherwise miss. Right. So total hit and miss will be total number of element. That's it. Anyone any doubt in list recently used policy?
So basically, whenever we remove something and put a new number, we call it a miss.
Yes.
Yeah, okay.
Yeah. Okay, so this is fine. Now the same question, instead of LRU, if I am using MRU, that is most recently used, then what will be the answer? Let's discuss that as well. Okay, so in this case, number of hit was 1, number of misses was 9. Now this was LRU. Okay, now we'll discuss MRU. Now, as name suggests, most recently used. Right now, what is most recently used?
The recent.
Recent one, right? The most recently used. That's it, right? So initially, my buffer is empty, right? The first element is 3. I'm going to add that. Miss.
Now
Second,
you add
huh?
it from down.
No, we can do anything from top or down. Okay. Yeah. But I mean, you should do like that only, not like that. First top, then down, then in between like that. So either from top, either from down. Okay, you can do that. Not an issue. So first, let's say you added 3, miss. Second element is what? 4.
4.
Again
4.
miss. Then we have 1, 4, 3, 1. Again miss. Right. Now next element is what? 4 here.
Hit.
Hit. Right.
Mm.
This will be hit only. No? So write it. Same thing will be there. So this will be hit. Right. Next element is what? 2. What will happen first?
It will replace 4 because 4 is the recent.
Yeah, it is going to replace the 4 because 4 is the recent one. So instead of 4, I am writing 2. Next element is 3.
1. It will replace 1.
But it's hit.
Two.
Why it
3
is
is
hit?
already
3 is
present.
already there, na?
Two. It will replace two, sir.
This is hit, na? 3 is already present here in the
Right.
buffer. Right? 3 is already present, na? Here like that. So it will hit, right? What about 1? We have this
1 is also present here.
1 is also present. Again hit. What about 4?
One will be
It will
present.
replace 1.
Now which one was most recently used here? Out of 1, 2, 3. Out of 1, 2, 3, which one is most recently used for
1.
the 4?
One.
Right, so we are going to remove 1. Instead of 1, that will be 4, like that, right? Now what about 2?
It's a
So
hit.
hit hit
Last
Hit,
two are
hit
sir.
hit.
hit
Yeah.
is also considered recently used. That means.
Yes. Yeah.
Okay.
What about this 3?
Hit, sir.
3 is already present.
So how many hit we have? 1, 2, 3, 4, 5. So we have 5 hit and 5 miss. Okay, that will be the answer in this case. So doesn't matter which sequence you are going to get, just follow this one in the case of LRU and MRU, right? So you can expect a question like this. So you need to practice your question. I think that will be better. MRU will be easier to remember, most recently used. Most of the students do mistake in the case of LRU, least recently used. Okay.
There will be 5 miss or 4.
1, 2, 3, 4, 5 hit. So 5 miss. 1, 2, 3, 4, 5 miss. This one is
Oh.
also miss. This one is also miss. Yeah. The total hit plus miss will be number of elements we have, number of blocks we have. Okay. So please try to solve few questions. You can refer to previous year questions.
Even in LRU, it will be the same. Hit plus miss.
Yes, hit plus miss will be number of element. That's it. Okay. So you can solve previous year questions from these two topics. So that will be good enough. Yeah. Okay. Any other doubt from this topic? LRU, MRU? Okay. Great. So what we have discussed, very two important topic. First one is binary search tree, and then one is LRU and MRU, and then third important topic is this magnetic disk. Okay, magnetic disk. So please watch the tutorial. You just need to note down the formulas for this. That will be good enough. Okay? These
Okay.
three are the important topic for this particular
Okay.
Yeah.
I joined little late. Magnetic disk was covered at the start of
No,
today's session.
not covered. In
Okay,
Saturday
not
session, we'll cover that. Yeah.
okay. Okay, right.
But please do watch the tutorial before coming to the session.
Yes, yes. Thank you.
Just the formulas are there. That's it. Okay. So these three are the important topic for week 8. Rest you can just go through the content and the slide. That will be good enough because all these things are you are going to learn in PDSA course again. Okay. All data structures part. But please do watch the lectures. I have just discussed how to solve the questions, right? If we have this particular concept, right? But why we required that, for which purpose we are using that, for that you need to watch the professor's lectures. Okay. Okay. So yeah, that's it from my side. Any other questions you have?
I have something from the week 6
Okay.
about um, multi-valued multi-valued dependencies.
Okay. What is your doubt?
Yeah, doubt is to make it a 4NF. When we make smaller relations.
Huh?
Okay, and that in that relation we say alpha multi determines beta.
Huh?
Okay, and we make a relation of alpha beta now. Okay,
Okay. Huh?
huh. So and we say that now alpha is a key, so this is in 4NF.
Yes.
But by the nature that it is multi-valued, now alpha will have values like 1, 2, 3.
Okay. So you mean to say only we have just two
Huh,
attribute here,
huh.
alpha and beta.
So for same alpha, we will have beta 1 and beta 2.
No, see, the concept of MVD is applicable only when it has, when a particular relation will have, table will have at least three attributes, and out of which two are independent. Okay, out of which two are independent. In that case, only MVD concept will be applicable. Okay, so at least three attributes, and out of which two are independent. If any relation is having only two attributes, let's say A and B, so this will be in 4NF always. 3NF, BCNF, 4NF always.
No, no, I meant set of attributes, alpha and beta.
Alpha and beta.
Set,
Okay.
yeah, set of attributes. So, like, professor has the slides have the. I will try to search and probably
Okay.
share. But let's say it was already something else. The relation was something else in which subject with instructor there was a multi-valued dependency or something.
Okay.
Uh, when we have broken down the relations into RIs, now the new relation is in 4NF we are saying, but that's not correct, na? I'll try to go to the slide.
Which slide can you do? Let me
Sir,
share.
in this case, when we break the relations into decomposition, so we get only unique values.
No, if we are saying the set of attribute, right? AB multi
Mm,
determines CD, right? Uh,
right.
this should.
So AB multi-determines C and AB multi-determines D, they will be different. And when we break down them, when we decompose them into different relations,
No,
so we get unique values only, for which we do a cross
can we
product.
write like this? AB multi determines in AB multi determine D. No, it is not a functional dependency. Na? You cannot write like this. We have different Armstrong axioms rule for the MVD part. Let me take the slide 6.5 or 6.5, 6.4.
I am also trying to search the slide, but I am not getting it. Lecture I saw it. There was a instructor
Okay,
and course
can we take
related.
this? What? So you are saying AB and CD we have this one, right? Combination of attributes.
No, no. In original relation, there was a multi-valued dependency,
Okay.
and when broken down, we got a 1A, let's say, and it is multi-determining something. Let's say course is multi-determining student.
Huh.
Okay, so A is multi-determining B in the resultant relation. So
Okay.
now course is having student 1 and student 2. So how course is a key in the new relation? I am saying it's not a key. No, it's no more a key. No,
Let me check.
it's
Sir, we had already discussed that in previous lecture. In this case, we take all the attributes to be the key.
Huh.
And the
This
unique
one.
No, no,
value,
but then
everything comes out to be unique.
no, the 4NF is not applicable then now on the reduced RI. It
No,
violates
that's
the
why we did
4NF
4NF.
criteria that
That's why we decompose it into 4NF. Na? When we break down into smaller relations, I have discussed this with that in the previous lecture we were discussing. The instructor, book, and that course
no, your
table.
let's say you're broken down and your R1 is course one column,
Hmm.
which multi determines students. So
Right.
course C1 has
This there.
student.
Yes,
See
sir. This is the table. Yes, sir. This was the
this
table.
one. Na?
So it in this case, sir, that the situation will be like that the two relations will be produced because they are both determining it, and we'll have both all the attributes as the key.
Huh.
Not
Only
not
they can
this.
uniquely determine the tuple. Na?
No, here
Repeated thing cannot determine
it
uniquely.
exists, right? Like this, because these two are independent one, book and lecture. Now, if you are trying to decompose this one, so
Okay, slide 29.20. Can you
this one.
one second? Where is?
So we have man, phone, dogs, likes. Okay. So man,
Now after normalization, if you see on the right, okay,
Okay.
the what is the second one? It is still, I think, man multi determines dog, right?
No, this one.
Second one,
FD
middle one, middle.
this one.
Correct,
Ah,
correct. So now the man, same man can have dog one and dog two, like right.
yes.
So the man is no more a key, na, in this reduced
Combine
relation.
is the
So
key. Man and dog likes combined is a key here. You can see super keys is combined here. You can see. So whenever you make a composite key here, let's say we have man and dog like. So M1 can have D1. M1 also can have D2. But combine is the key here. Combine is unique here. Okay.
but 4NF criteria said if M multi determines D, then M should be a super key. Then that
But
statement is wrong, na?
for that we should have at least three attribute, right? Here we just have two attribute, right? Dog likes. That's it.
No, probably I'm not able to convey my doubt. See, 4NF criteria. Let's go by 4NF criteria. 4NF criteria says
Uh,
if alpha multi determines beta, alpha should be the
key.
super key, right? Uh,
Okay.
so if this is 4NF decomposition, man likes dog, man multi determines dog is not meeting that criteria. That
What
was
is
my.
the FD here? What is functional dependency here? So it's a multi-var dependency. We don't have FD applicable to this particular thing, na? There is no functional dependency applicable to this. There is FD applicable to this man and address. You can see. Okay. So this is not FD. This is not. We cannot say man is determining phone. This is not correct. Here we can say man multi-determine address. This can be possible, but reverse is not true, right? So here we are not talking about the MVD. Here, if you see, we don't have functional dependency here, right? If there is no functional dependency to any relation, then combination of that particular attribute will be a key in that case.
No, no, how we got the key, I understood.
Huh.
But to check for a 4NF, for this relation, man dog like only that relation,
Then what is this multi-determinant, the super key?
the, the man is no more a key in this reduced table. I want to say that because man uniquely is not determining the tuple. So man is not a key. Combined key, I understood, but 4NF doesn't say uh, alpha beta together have to form the key.
But
4NF
here we
says
are saying man determines dog likes here in this case. There is no FD na, for this relation. This is not applicable here, right? Man determine dog likes.
I got it. Okay, ठीक है. Man determines dog like is not a key. Is not a dependency here. Understood.
Yes.
But man is not the key also, no?
Yeah.
So how does it? How is it in 4NF?
So this relation is just having two thing, right? So two attributes. So by definition, MVD is not applicable to this one. So any relation having two attribute, MVD will not be applicable, right? Also, if you see man, dog likes, and let's say we have the third attribute, but there is dependency between dog likes and that attribute. In that case, also there will be no MVD. Okay, because there is no independent attribute here. Anything. If there is dependency, let's say we have P. So if there is D1 determine this dog like determine P, if it exists, then this MD1P will be in 4NF. There will be no MVD here. Even we have a multi-determined DL in this case. If third element is there, but there is no independent attribute, then we cannot say. Then it will be 4NF. No MVD will be there.
Mm,
So
no,
your question is for this relation, man is not the key, right?
my question is how to check for 4NF.
Yeah. So first for 4NF, first
How to
condition.
check the second condition is being violated or not. First condition is it is a trivial MVD,
Yeah, it
right?
should be
That
in
is
BCNF. So basically, left hand side must be a key, right?
okay.
So left hand side must be a key that is for BCNF, and then after that we are checking no multi-value dependency, right? This is the condition for 4NF. So left hand side should be a key, or there should be no multi-value dependency. It should be in BCNF as well. So if you see, we have this example. We have this four attribute. Now we have decomposed that four attributes into these three relations here, like that, right? Now if you observe, none of the relation is having more than two attributes. So you can see here MVD concept will not applicable, right? In the opposition, both MVDs X is a man, which is again not a super key. Out X, so man and phones together. Yeah. So here you can see. Yeah. So after normalization, if any tables having just two attributes, it will be always in 4NF. That's it. So I'm not. You are saying why man is not a key here, right? This is your question.
No, no, no. My question is checking for the second condition of 4NF. Just by 4NF, let's say we don't know whether it's BCNF or not. Okay. 4NF conditions say if there is a MVD, it should be trivial. Okay. And second condition is if alpha multi determines beta, then alpha should be the key.
No, no. Alpha multi-determined beta will not be there. Where is?
Yes, yes. I think top only. Yeah, here. Ha. Alpha should be the key.
Okay. Alpha is the super key for schema R.
If one of these is satisfied for every MVD, it's a 4NF.
So alpha is
So
determining the alpha is a super key in schema. No? Alpha beta where man and dog like is a super key. That becomes alpha. That is a super key for schema.
no, how
Yep.
alpha is distinct from beta, no? Now you are mixing beta with alpha.
No, alpha beta set. These small alpha beta they are set. I am taking alpha as the set of man, comma, dog like. That becomes alpha, and that is a super key for a
No,
schema.
then
That's it.
alpha, I mean, man, comma, dog determining what? Nothing.
Yeah. So here you are saying
Man,
man
comma, dog like
determines
is a
dog
super key
like,
na
right?
alpha.
No, you are. Wait. You are also trying to convey something, but let me.
No,
Yeah.
see,
So
there are
your
two
question
two
is this
types
one,
of things.
right? Hello.
See, yes, treat man as alpha and dog likes as beta. Okay.
Yeah. So this
MVD
is
will
for
not apply because that's what sir said. Na, there are only two attributes. MVD will not apply here. It's already in 400. That's
MVD is
what's
not applied.
saying.
See the definition of MVD here. So where it is, we have
Huh.
discussed those four relations. Yeah. So for a relation, MVD alpha determine beta holds on R if any degradation R for all the pairs tuples T1 and T2 is
No, I'm not saying. I am not saying that there is a MVD in this man dog like relation. I'm not saying that. I am saying
uh,
having come down to the reduced relation,
uh,
now man determines dogs like. In that, man is not the key, which is the second condition of the 4NF. Or does it mean that? See, either of the two conditions has to be satisfied, right? If there is a MVD present, then that MVD has to be trivial.
yeah. So MVD is not present here, right?
Not present. MVD actually okay. MVD is not present because we don't have the third attribute. Okay? So So forget about the triviality or non-triviality of the MVD. Now coming to the second thing where man should be a super key. Now that also we cannot check because uh,
No, man
there is no MVD. So
multi-determine dogs like, right?
yes, yes.
Yeah. So if there are no FDs, so what we are seeing here, combination will be a super key. But your question is left hand side is not the key here, right?
Then individually I'm understanding
Uh,
the concept. Combination is a super key. So that's okay. Basically this relation is nothing but a key. Ri, this is a Ri where Ri is equal
uh,
to K and
yes.
K is the key, right? But what is the meaning of the second condition then, which was specified by the for the 4NF? How do we check for the second condition? So does the second condition necessitate that in the reduced relation there should be a MVD present also, and if it is not trivial it should be like this? Does that uh, somewhere yeah. So
Yeah.
second condition necessitates that MVD should be present,
Uh, MVD should be present.
because alpha meaning of alpha means there is alpha in the reduced relation also. Let's say if when you decompose.
Yeah. So if you see alpha
So
multi-determine beta here, but B and C are independent, but we are here dependent. In that case, you can see MVD is also present and left hand side is also super key, but still it is in 4NF, right?
okay. So okay. So to check the second condition, we should have a MVD first in the relation, right?
So
And
do
it
we
should be
have?
non-trivial MVD. That's the meaning of entire 4NF checking, right?
Yeah, so you can see this man and address is given to us. If I add man, dog likes and address together, so here we have MVD, right? But here we what say we don't have
Uh,
it is in 4NF, right? Even though we have this MVD, it is in 4NF. Now, if you check for that condition,
no, I would not. No, with the condition, I will say this is not in 4NF
yeah, sorry,
because
yeah, dog likes determine address is there, man determine address is there. Yeah, we want dog like determine address. Yeah, this will not be the 4NF.
no man is not determining a full tuple entirely. So okay, in that relation, then if dog like totally determines address, um, then probably that will go to MNF. Sorry, 4NF.
Yeah, dog likes
Means
determine address, then we can say man, dog like, and address will be in 4NF.
4NF, because man dog like is a non-trivial dependency, MVD, but still M is a key because M totally determines the tuple uniquely. Because dog like determines A.
Dog likes
So
and
for
dog
every dog there will be a unique A.
yes. If we add DLA here, so for D1 only one unique address should be there, right? So this will not be
Still
present.
M will not be the key because two M1 and
No, how we are finding the key here? We are not considering MVD for finding out the key. We only consider functional dependencies to find out the key.
understood. But so man
Then,
dog like and address is still not in 4NF, no?
then man determines address is a functional dependency, isn't it?
Yeah, here we have make a separate relation for that, right? You can see here, right? So see, every relation having just two attribute A and B, there are only two possibilities, three possibilities. Either A can determine B, or B can determine A, or both, right?
Okay.
In either of the cases, left hand side will be always a key. If only A determine B is there, in that case A will be a key. If B determine A is there, in that case B will be a key. If both the things are there, then in that case A and B both are the keys, right? Both the left hand side will be a keys. But if there is no FD, in that case it will be a composite key. If any three or any two is not present, then in that case composite will be a key here. That's why we have made the composite key here.
Okay. No, but I'm somehow not convinced with the second condition. If there is a non-trivial MVD, how to go about checking the second condition? That the left-hand side of the MVD is a super key. How to check for that? Or at least a counter example is not coming to my mind where alpha multidetermines beta is a non-trivial MVD and alpha is still the super key for the relation. Uh,
Okay.
This
Have we discussed one example here? Restriction that
there was one example. I
alpha
don't
is
know
a
how
okay.
I'm.
Take if A is super key by using attribute closure, right? If not, then choose a dependency in F plus that breaks for an F rule states A multi-determine B. Okay. So this is what we are doing here. If you calculate, that is fine. Okay. Create R1AB. Yeah, this is what we have done. So if we have MVD, we'll create a relation for that, right? So see, in that case, there will be no concept will not be applicable. Even though we have A multi-determine BC, we can still have ABC. That will be in 4NF because we don't have any independent attributes in that case. Okay. So
Okay.
here also while decomposing, we always take a closure of left hand side and we'll make it as a one table. That is how we discussed in the previous lectures. Okay.
Okay. Just hold on. I'm trying to find out this thing. If
Okay. You can check and let me know if you get some example. Okay. You can tag
okay,
me on
okay.
Discourse at Piyush W.
Right. But my question you understood, no? Like
Yes.
second
Uh,
one is decomposition. Okay, that's fine. But um, the con- checking is saying that alpha multi-determines beta. It's if it is non-trivial, then only we are going to go to the second condition, the second check, right? Second check is alpha is a super key or not. So alpha determines beta MVD is existing in the relation, and it is non-trivial, and alpha is key also. So that somehow that example is not coming to my mind.
no, if we consider this particular case, A having three attribute, A multi-determine BC, in that case, what will happen? This is the key, and we are saying A, B, C. So this will be in 4NF, even though we have MVD, right? This is example, na? Left hand
Ah,
side is
correct, correct. Okay, okay. Okay, it's non-trivial and okay.
you can see
So
left
here
hand
A
side.
is a key because it's determining.
Yes.
No, no, no. No, no. Now A multi-determines BC. So BC together may take more than one values for the same A because A multi-determines BC, na. So A is still not a super key for the relation ABC. Yeah, this is a good example now. I got probably I can ask much clearly what I. So alpha has to be key, super key, right? As per the condition, not the ABC together. So if A multi-determines BC means for same A1, I can have a B1 C1 and a B2 C2, two tuples. So A is not a super key, na? So how ABC is a 4NF?
Yeah. So here you can see we don't have any dependency between B and C. Okay. So here we are assuming we don't have dependency between B and C.
Okay. So let's say there is a A1, B1, C1, and because A multi-determines BC, there is a A1 again with uh, B2, C2. So definitely A is not the super key. That is clear.
I will check with that concept because super key concept applicable to functional dependency, right?
Correct. So
Yes, sir.
some
Sir, even in this example, you can break this table, sir, and we
Yes.
can actually 29.9.
So here you can see we can say this will be true, but reverse is not true here. We cannot say that will be a true, right? Yeah. So
so that those even the identities are clear to me, but the checking for 4NF part is not clear.
No,
Alpha is never going to be the super key. That's my whole argument. Is that the moment alpha is multi-determining somebody, the alpha beta relation is never going to be the one where alpha alone is going to be the super key.
yes, right.
So then why check for alpha to be super key? So
Yeah. So as of now, you understand like what we have discussed in previous case, how this came. So whenever
okay.
you see this alpha multi-determined beta, just remember one thing: if you want to check or if you want to apply all those conditions, take any two tuple such that we are having the same alpha value. So take any two tuple having same alpha value, but such that they should be different beta value. Okay, so alpha value must be same. Take two tuples such the same alpha value but different beta value. Okay, different beta value, and then you need to swap those value between two tuples. Swap the beta value. For example, if you say course and book, right? So I will take this one as T1, this one as T2. I will swap this beta value here. So instead of Silverstat, it will be another pill. Instead of another pill, it will be Silverstat. Now I got two new rows. AHA, this Netherpelt, John D, T1. If these two rows are present after swapping in the same table, then we can say MVD exists. Otherwise, MVD does not exist. So if you see AHA and John D, T1, so John D, so it will be here. AHA, Silverstat, William M, this will be like that. Okay. So if this
Yes. Yes.
condition satisfied, then we can say MVD exists. So keep alpha value
Yeah.
same, exchange the beta value. But we have to check for every unique alpha value. Every unique alpha value. So what we have done for AHA, now check for OSO also here, right? Now again same thing. Anyway, we have the same Silverstat. Even if we swap, same rows we are going to get. Now in this case also for book lecture, if you swap, so you can see OSO Silverstat William D, OSO Silverstat John D. So anyways, we are going to get the same two rows, right? So whenever you swap the beta values, you are going to get two new rows, and those rows are present in the table. Then you can say MVD exists. That's it.
Yes. Yes. MVD is clear. But how to check for 4NF? No, that I am not confident right now.
Yeah. So for
At least from the conditions that are given for 4NF checking,
yeah.
whether a relation is in 4NF or not. So these two, yeah, these are confusing me.
Okay.
So alpha multi-determines beta, and if it is not trivial, then we are going to check the second condition. So alpha multi-determines beta itself is telling that alpha is not a key in the traditional sense, right? So then how alpha beta becomes a 4NF?
Alpha
So this
is
is
the
where
super
I'm.
key of schema. So when we say alpha is super key of schema, it means what? Alpha will give me alpha determines all the attributes from the relation R, right? This is what we
Yes.
can say.
Yes.
So in that case, alpha will be a unique one. But here if we apply alpha multi-determined beta, I will check with this condition.
But sir, just now when you did the swapping,
Uh,
the swapping shows that it determines all the tuples, isn't it, in the table, even after swapping. When you see the multi-value dependency, you apply this. When you swap it also, so course eventually it determines all the tuples.
yeah, so no, course does not determine, right? So AHA, we are saying syllabus at AHA middle belt. So here you cannot say, right? Will not get that. So when we get this rows now after swapping, so we can say MVD exists. So we are checking MVD exists or not. If MVD exists, then it is not in 4NF.
Okay.
Okay. So if that condition getting satisfied, is anyway we are checking for these four conditions only here if you see, right? So in that case, MVD exists and it will not be in 4NF.
Sir, even
No,
with
no.
this example,
So maybe those
MVD
rules
can
are,
exist, and
I think those rules are for the normalized table then, to check if it is in 4NF.
Yeah. So if I want to normalize this particular table, right? So how I'm going to store course book
Course book.
one relation and
Yes.
course lecture will be one relation, right?
right, sir.
So this will be my normalized table, and you can see here for course multi-determined book, left hand side is the key for this relation, right? if we have key means
Sir,
like
both will be, sir. Both
No,
will be.
together it will become a key, super key.
together it will be a key, right? Yeah. So if you say course and book, so AHA and Silberstadt will be there.
Yes, sir.
AHA, Netherpet will be there.
Netherpet.
Again,
Oso and silver, sir.
Silberstadt will be there. Like
Oso and silver.
yes, also and this will be there, right? Like that.
Yes, sir. So this will be one.
Huh?
Oso and silver, sir.
Yeah.
Third one.
One more thing will be there. Also and Silberstadt. Yeah. Right.
Yes, and for the other table, sir, we'll have the same, like, but we'll have that
Course and lecture.
AHA and John D,
John D. AHA
AHA William,
M, and here again
AHA Christian G,
yeah, AHA
Christian
Christian
G,
and
and
OSO
also John D
William John D
and
and
William.
MM. That's it. Now when you join this table, you are going to get this entire table, right?
Yes, sir, and it will be natural join.
Yeah, natural join. So
But then your course is not the super key. The super key will be course and book.
now in this case, both table are in 4NF, right?
Right.
Yeah.
This is the decomposed 4NF form that we had discussed earlier in the previous lecture with
But
Isaac
still,
Krishnan.
course multi-value determines books, no?
Yeah.
हाँ
So
तो
that
दिख तो रहा है ना 2AH 1AH 2 values B,
But then
that's
how
what
can it
the
be in
multi-dimensional.
4NF?
So, sir,
It's not.
sir. So from course and book, see, from course and book, the MVD, original MVD of course multi-determining book has vanished because now this is in a proper set theory. Unique tuples are there course book mein.
combine.
Okay, so correct. So this understood. There was a multi-dependency when along with book there was a lecturer in original table. Lecturer removed, you just have one-to-one relationship between course and book. Not one-to-one, tuples are unique in course book. Okay, so now course book table doesn't have any MVD. So course is a key. Okay, understood. No, our course and book combined somehow. Okay, but the definition or the criteria to check the 4NF is written in such a way that it says alpha multi-determines beta is also existing in the relation and it is non-trivial. Now you have to check that alpha is a super key or not. So this is where I'm getting confused. Here
These four
conceptually I can
are
understand course book is a
these are the conditions to check whether table is in 4NF or MVDs exist. After that, we execute those conditions to break it into the normalized form. No?
No. Here we are checking for 4NF only for these conditions, right? So yeah. So
so these conditions are confusing us. So
Sir, in that
so even your
normalized
course book example also now AHA the course there are two
occurs
books.
twice. Yes. So isn't it multi-value?
Correct. So now AHA is not a key of the course book. Sorry, the course is not the key of the course book table.
yeah,
So how are we
nobody
saying
said
course
it,
book
no?
table is in 4NF?
No, it combine is a key, but according to that condition, right? So
We have broken down, right? We have broken down and made course book and course what
see,
lecturer.
I guess definition like what we have discussed. So for MVD to be exist by definition, there should we have at least 3 attributes. That's it, right? If there are only 2 attributes, the concept of MVD is not applicable to that.
Oh, okay.
Exactly, sir.
So concept of MVD is not applicable to the relation having 2 attributes only. Okay.
Okay.
Discuss, right? So
But it's not mentioned here anywhere that
not
condition.
mentioned here. Yeah. So three attribute not empty set possible one behavior.
No, that is one thing. And another thing is if course book doesn't have a MVD, course book has a MVD, you know.
No, there are no 3 attributes.
MVD doesn't apply
No,
to
3 attribute.
it should have at least 3 attribute, then only we can say concept of MVD exists.
Okay, so if course book doesn't have a MVD, then how do we check for 4NF?
It's already in 4NF.
It's already in 4NF.
Any relation having
How?
So there is no MVD na here, you can see.
Course uniquely identifies, determines every book.
So if if any relation having 2 like that, so concept of MVD does not exist. It means MVD is not present, right? So there will be only two cases: either A can determine B or B can determine A, or none of the FDs are possible. In that case, combine will be a key, or in either of these cases, A or B will be the key, right?
So your B will be the key then, book.
No, here combine will be a key in this particular case. Composite
Okay.
course and book will be composite key will be here like that.
Okay.
Okay. The concept
So
of
this is a table with no dependency. Basically, course book is a table with no dependency.
dependency. So in
No.
that it will be composite key.
Okay. So then most of the 4NF decompositions will turn out like this, where
This only.
there will be only that set of attributes who are not determining anybody. Combiningly, they are the key.
Yes. So whenever we
Then
say
that, okay.
A alpha
Okay.
will determine beta, so alpha beta will form one table, right?
Okay. So if MVD is as such going to get eliminated in the reduced thing in the 4NF, then in the 4NF there should not be a comment. In the 4NF checks, there was no need for comment of a MVD, no, which we saw the slide which you highlighted, or my doubt also.
There may be if it's a table with many attributes. I
For
think so.
attribute is not correct, but for I will check with this, right?
Yeah. So if you could just elaborate more how to go about this, checking these two conditions.
Yeah. So
Okay.
what we said, at least three attributes are required, and out of which two must be independent. Because if it is dependent, it means what? Either B determine C or C determine B. In that case, you cannot have those tuples, right? So MVD condition will not get satisfied. So at least three attributes are required, out of which two are independent. Only then MVD condition will be applicable for those things.
What
And
do you
sir,
mean? What do you
sir,
mean
even
two are independent?
So
sir,
for
even
yes, even
sir, even for these conditions, first one is for MVD, second is for functional dependencies. If we look closely,
Arre
first
no,
one
yaar.
is used to
First
check
one
for
is for
MVD.
no.
This
First
super
one
key
is
concept is
checking
not applied in
triviality of
MVD.
the.
Super key is not applied in that.
See,
Nah. First one is for MVDs. Second one, super key is for functional
what
dependencies.
is first one? Can you read the first condition?
MVD. I have read
key
it.
here,
Alpha, beta, and beta is for
whatever is
that.
there alpha, so that should be a key here, right? But to
If
find the
if
super
if your alpha determines beta is trivial, then you can say your relation is in 4NF.
yeah.
If at all there is alpha multi determines beta, MVD is there on the relation. Okay. So this check is saying that if there is a alpha multi determines beta and it is trivial, okay, you can categorize the relation as 4NF. If not,
Either one
okay,
has to be true, no?
No, so
true, correct,
the trivial
correct.
is
So
the
that's
anyway condition for all the case, right? So if you look at this particular thing, alpha is a super key for a schema R, right? So we need to see one
so
example where
Sir, can you explain that independent attributes? I didn't understand.
understand the concept first. MVD
Sir,
will be
these
applicable only when let me complete. MVD will be applicable only when we have at least three attributes, and out of which two are independent. Okay, out of which two are independent, right? So it can be there. We have five attributes, and out of five, we have two independent, and MVD will exist. We may have 10 attributes out of 10. If any two are independent, then MVD will may exist, right? Now, if you consider this particular example, A, B, C. Now, when I say independent means what? So when I say A multi-determine B and B and C are independent, it means B determine C or C determine B is not applicable to that particular relation. Okay.
Okay.
correct.
Sir,
Mm.
sir, even in this question, sir, this is for the decomposed form. We have to check whether something is in 4NF, right? When I go for the man, dog like, and man
No, 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 no,
situation,
no, no, no,
listen,
no,
listen, just listen.
no.
Let
This
me
is
complete
just
first. Please let me complete. Please let me complete first.
no. Your
This is
first
for the decompose.
statement itself is wrong, na.
Nah,
It is
listen to
not
me
for
now.
decompose.
You read it now. A
Arre Baba,
relation
it
is
is
in
not for
4NF.
decomposition.
Please let me complete first. Please just let me complete. A relation
Ah,
is
then it
in
has to
4NF.
satisfy these two.
Please,
Huh.
at least listen to
Okay.
me first.
Just
First relation is in 4NF. The previous were the conditions to check whether MVD. When we have MVD, we break it into 4NF, and these are the conditions to check if the relation or schema is in 4NF or not. Alpha multi determines beta is a condition for 4NF, or alpha is a super key for schema R. That is like वो क्या कहते हैं that condition for that. In man dog like situation, we have three tables: man multi determine dog like, and the other one is man determines that, right? Just see it carefully.
Sorry,
We have both
your
situations.
reading of that para itself was wrong.
नहीं,
You are
नहीं, अरे
saying
ये
that a relation
all the
is in
same.
4NF, not this.
Just
I'm
listen
saying.
to me. Let me just complete.
Are
No?
after listening to you only, I'm telling here.
Just listen to. No, that's what I'm saying. No? Man multi-determines phones. That is the first condition in the decomposition of 4NF. Man determines address. That is the second condition for the schema to be in 4NF. These are decomposed after decomposition. When we check for these conditions, they should satisfy. Then it is in 4NF. That's what I'm saying. That was
Okay, can I
that's
ask you a
what the
question?
paragraph
Can
says.
I ask you a question now?
Please.
Man determines dog like is in 4NF?
And MVD.
No.
It's a MVD, and
Man.
if all the conditions are satisfied.
You explained. No. Now my question is.
It is 4NF. It is in 4NF. It is in 4NF.
4NF. No.
It is in
Now
4NF.
go back to the 4NF slide.
No.
And
See,
read the
4NF.
4NF definition which you read.
Okay.
Go ahead. Please go ahead.
So if you see here, I will check this particular thing here. You can see alpha is a super key, right? In that
Sir,
case,
man is.
Sir, I am
it is
convinced. You
for-
got my
after
point.
The decomposition, after the decomposition, that is in 4NF. No, these three tables are in 4NF. That's what I'm saying. And we have to check whether these are in 4NF. First condition is alpha, man multi-determines phone. That is alpha multi-determines beta. Second one is man determines gamma. That is man determines address. Both are satisfied. That's what I'm saying. That's why it is in 4NF. This is not
See,
this
why you
after
are bringing?
decomposition.
no. See, no.
How does address go into the dog like now? You are already decomposed. Now just focus on the decomposed thing. So
No. See, wait a minute. I got your point. If you are saying this is in 4NF, it means there is no MVD, right? It means that this should satisfy man multi-determine dog like, right? It means that man should be a super key, right? In this table.
Sir, either
Yes.
it's either of the situations, sir. Either or, either this or either that.
But
No,
anyway,
instructor was emphasizing if my question is that or not. He was not disagreeing with you. He was telling my question is that man is super key or not. He was confirming that, I think.
Yeah.
Yes, sir. My question is that the left side should be a super key. That's what your conditions bring out. I don't know. The conditions say that you are checking a relation. The LHS has to be a super key, or else the MVD should be non-trivial.
Yeah. So
if at all there is a MVD.
Yeah. So what I said, concept applicable to only when at least 3 attributes are there, right?
Correct. So let's say beta is like probably B and C together. Okay.
A, B, C, right?
Huh.
Now here, this is alpha, this is beta. Now, when I say alpha is a super key, right? So A1.
Or maybe let's take a D as independent also, and then say ki A multi determines BC is a MVD.
Then MVD will exist, na? Okay. If D is independent with either B or C, then it will MVD will exist. In any way,
MVD exists, then only this check makes sense, no? The check of whether MVD is trivial or not.
No, that is the condition for 4NF, right? If MVD exists, there is it is not in 4NF, right?
No, it doesn't say that. That full para, if you read, if it is in 4NF, MVD can totally exist if you go by the. See, if the relation is in 4NF, the dependent is set or its closure, yes.
Right?
Huh?
MVD will exist, but this should satisfy, right? This is what.
Yes, this should satisfy. If either it is a trivial MVD, if it is not trivial MVD, like A determining BC, let's say it is not non-trivial in the ABCD relation. Okay. And if it is non-trivial, then A should be a super key. But I am not convinced with the second part. If there is a MVD, how can A be a super key? That is where my.
Okay, I will try to come up with the example. Okay.
Right. Thank you. That will be great because this is little.
No, I got your point. You are saying if we are saying this A, B, C, and let's say A multi-determine B, but anyway, A is a super key they have mentioned, right? So it should uniquely determine this B and C.
Yes. Which is not possible if we come down to a relation of ABC, just ABC. That A couldn't be a super key, right? And A determines A multi determines BC is also not trivial. So now ABC is not meeting any of these criteria.
But still, it is in 4.
But trivial hai. Sir,
I don't know if it is in 4. If you ask me to check with the conditions, I would say ABC is not in 4NF.
But alpha
if you just
union beta
ask
is
me
R,
to go by
that's
these.
the trivial situation. If you look at it,
sorry?
alpha union beta. The second condition for triviality is alpha union beta should be R. So A union BC is R, na? So that's it trivial.
Huh.
How
In
can you
case
miss this
we can
point?
see alpha union beta. Yeah.
That is why I wanted to take the D as an independent attribute and check.
In that case, it will
So
not be in 4NF now, because MVD will exist there, right?
okay.
Consider D as an independent attribute.
Huh. Okay, this was a good point by the other student where he mentioned no alpha union beta is probably this making R and this thing. So
So here
thanks for
also
that
same thing
clarification.
is applicable.
So
Na? Here
if
also same thing. Na?
okay, it is becoming a trivial MVD. We are saying.
Yeah.
So all these decomposed relations are satisfying the first condition itself.
Trivial. Yeah, we can say.
Okay.
MVD
Last one is satisfying the second condition.
yeah,
Last one.
man
It's
address.
an FD, it's not an MVD, so it's satisfying the
Having
second condition.
FD, right?
It is a normal dependency, no? Not a MVD.
Now, if you consider any other attribute, then MVD will exist. If we are talking about D, then MVD will exist if we just have this one, because it would be independent with either B or C, right?
So now how will be the testing if D is there?
If we have A, B, C, D, then check for MVD exist or not based on this one. Whatever I have said, just swap the this beta value and check whether you are getting the same beta value or same rows, two rows or not in the table. Okay. If MVD, if we got the same rows, then we can say MVD exists. It means it is not in 4NF.
Okay.
Okay. So yeah, first condition will be
So
true.
most likely ABCD will not be in 4NF if there is a MVD like A to BC, right?
A, B, C. Yeah. If
And D is also there, but there is a multi determines BC
Hmm.
and D is independent. So most likely ABCD will not be in 4NF. That's what it's coming out to be, because A multi determines BC is never going to be trivial.
Yeah. So if you see in practice assignment, we have discussed one example in previous session, right? Same thing we
Okay,
have
sir.
discussed, right? So instead of that attribute, if I just add that attribute, in that case it is in 4NF, right? You can watch the previous session. In that we have
Okay,
discussed.
okay. Thank you so much. Yeah. Sorry for taking some time on this
Yeah.
because after listening lectures it was a little confusing for me. So
Okay. Thank you. Thank you everyone.
Sir, I have some queries, sir, if you don't
Yes.
mind.
Quickly. I need to close
Sir,
the
yes.
office also. Yes.
Yes, sir. Sir, in quiz, sir. Sorry,
Quiz one.
graded assignment. Yes, sir. Graded assignment.
Okay.
Sir,
Which
there's a question.
which week?
Just a minute, sir.
Yes.
Hello.
Yes,
Hello.
tell-
Yes, sir. There was some network lag, sir. So question number 8, graded assignment 6.
Let me share my screen. Question number 8, na?
8, sir. And sir, I would like to apologize, sir, if my voice got louder during the discussion
No, it's fine.
because there was.
Yeah, I'm unable to get your point. What you are saying? Yeah, your point was correct.
Yes, sir.
Question
It's all
number.
written there, sir. We just have to written right carefully.
Okay,
8,
sorry.
sir. Question 8. Question 8, sir.
Week 6, na?
Week 6, sir.
Question 8. This one. Yes.
Yes, sir.
So here we are saying we have schema D having this attribute. We have functional dependency D1 decomposition D2 such that D1 intersection D2 is not equal to empty set, right? So it
Yes,
means it is a lossless decomposition. Okay. Then D1 and D2 are okay. So same thing we need to find out now. First, find out the key. Which one is the key here?
sir. From F though I can see all other keys like individually or are keys,
Yes.
candidate keys.
P say Q. Yes. P say Q. Yes. Q say R. P say yeah. All
Yes,
four are the keys, right?
right, sir.
So it means what? BCNF condition gets satisfied. Left hand side is key for every functional dependency.
Sir, but if we break it into D1 and D2, so in that situation, तो फिर तो there is a transitive वो क्या
In
transitive वो for example, if I break down this relation into PQR and RS.
PQR and RS. Okay. So
Yes, sir.
okay.
So from PQR तो I get PQ to QR and from RS to get RS. RS तो I got it. चलो वो तो है. That is fine.
Uh,
But PQR वाले में sir.
in PQR, the applicable will be what? P determine Q and R. In Q determine PR and R determine PQ. All three will be there. So in all the cases, all three are the left hand side is the key, right? In PQR, P determine QR will be there. Q determine
Yes,
PR
sir.
will be there. R determine PQ will be there because all the applicable functional dependencies, right? So in all
तो सर
cases, left hand side is the key.
तो सर in such situations तो we'll have to like I will have to go for F plus and
Yes,
D1 plus and D2 plus, right?
yes, yes. No, D1
अच्छा
plus.
तो
What is D1
पूरा
plus?
एक्सपेंड हाँ जी
What is D1 and D2 plus? Sorry, I'm not getting.
सॉरी F फंक्शन D1 फंक्शनल डिपेंडेंसी प्लस F प्लस ना
Okay,
कंप्लीट लाइक
right, right.
तो सबका मतलब मुझे सब कुछ आई हैव टू लुक फॉर एवरी प्लस लाइक F प्लस D1 F प्लस D2 F प्लस
All possible functional dependencies applicable to D1, that is F1 plus.
ओके सर फिर दैट शुड बी लॉजिकली एवरीथिंग शुड बी लॉजिकली एम्प्लॉयड
And this thing is applicable for dependency preservation also. Okay, so you need to find out all possible functional dependencies applicable to that relation for dependency preserving. Okay,
सॉरी सर प्लीज कम अगेन आई डिडंट गेट यू
for the concept of dependency preserving, if you see week 5 concept, in that also we are doing the same thing. First we're finding out F1 plus, right?
राइट सर राइट
Yeah, so that is the case. Like all the possible functional dependency applicable to R1 based on the parent functional dependency you need to calculate.
राइट सर राइट
Yeah.
राइट राइट
So here, if you
एंड
see P determine Q is there, but P determine R is not mentioned specifically. But if you apply PQ and from QR, you can apply P determine R, right?
राइट सर
Yeah.
It's also basically these are both in 2NF and 3NF.
Ah, yes. BCNF as so that's why 2NF and 3NF.
Right, sir. Right. I just got confused regarding that, the FTs. So I'll remember that, sir. And sir, quick question, quiz question, sir. I had some queries in that.
Okay.
Quiz one question, sir.
Which one? Yeah. Can you open?
Yes, sir. Just
Which question can you tell me? I think we have if that question belong to that case study kind of thing, many to one, one to many. Is that a question?
no, no, sir. This was regarding that. Except all, sir. Like
Ah,
student and ID are given. So
so in
I'll
that
just
case,
open it, sir.
I can say I remember one question. So like first there was a bracket, right? Okay, can you open that question? I am stop sharing.
Yes, sir.
Don't have access to that.
Yes, sir. I'm open. I'm just sharing my screen. Just sharing my screen. Ah, yes. So should I share my screen, sir?
Yes, yes.
Sure. Sir, is my screen visible, sir?
Ah, yes, now visible.
Yes, sir. This question, sir.
Yeah, so select ID from student course. So 5 into 4, 20, right?
Yes, sir.
And accept all select ID from a student.
Right, sir.
So here 5, not 5,
Right, sir.
20, yeah, 5. So ID will be what in that case, except all will remove.
Oh, single, sir. All 5
Yeah.
instances only
So
individual.
15 will
Yeah.
be there, right? In the output.
Yes, sir.
15, then after accept select ID from student. That is again 5.
Again, sir.
So all
Right,
it will
sir.
be all the instances na, from 15. So output
Right,
will
sir.
be 0, I guess. 0 na.
अच्छा, okay. Hmm.
Except तो सभी remove कर देगा. Doesn't matter. Yeah, actually.
Okay, so I think I read it all except all.
Okay, then chalo. Thank you.
Thank you, sir. Thank you so much, sir. And my apologies, sir. Sincere apologies, sir. Thank you, sir. Thank you so much for the time. Good night, sir.